off we go. So, okay, we're on chapter 15 now, guys. I'm going to try to stretch these out potentially to 3 lectures. We'll see. At least 2. Because we're getting towards the end of the book. That's exciting. Where are we? Do I have the book open right now? I do not. But there's 18 chapters. That's it. So we're almost to the end. Though chapter 17 is going to take like a while. I think that's the most action packed. We're just getting ready for that essentially. This is like the preface to it all. It's like it's very exciting. So yeah, hopefully if you read ahead, you'll understand why I'm excited. But let us talk about predicting things because we've learned how to we've got data, we've tested hypotheses, we kind of understand how to ask questions and get answers from what's happening right now, but we haven't quite learned how to say what's going to happen later, try to figure out, infer what's going to happen later given data about things happening right now. That's the goal. I'd like to predict the future. All right, so this is chapter 15. Please start reading that. A lot of interesting things and important stuff to talk about. So yeah, here's the first idea. I kind of want us to pause and at least ponder this, if not in groups with people sitting next to us by ourselves. But our goal is to predict the future. We would like to figure out something that has not happened. We'd like to figure out the odds of something that has not happened given stuff that we know. That's the goal. All right. So, for example, let's take TikTok because we're probably all on our phones all the time. So most of us in the class probably have TikTok. TikTok knows all the videos you've ever liked and the ones that you've watched longer than others, the ones you don't swipe on, right? And so when a new video comes out that somebody publishes, somebody posts a TikTok, how do they know to give it to your phone? How do they know to put that on your TikTok For You page? How do they know that you might like that one? Because usually you do, right? Usually it's good, right? The algorithm's right. How do you think they did that? They have some data on you. What do you think happened? Try to discuss that, or at least ponder it. If you can, talk to people. What are your ideas? How would you program this? You can use generic words. Human. Because you share videos with your friends, right? How do you know that they're going to like them? Similar idea. I still need to do that. Yeah. Another minute or so to discuss. Why do you know that a video you shared with your friend, why they're going to like it? You have some knowledge, right? You have some data. All right, our voices are starting to die down. What are our thoughts? Like, how would you program TikTok if you could like? What do you got going on in your head when you're sharing a video with your friend? Why do you know that they're gonna like it? What knowledge do you have? You have some data, right? You're doing an analysis technically. What are you doing? Can you explain it?
Based off of like previous knowledge I have of the friends and the jokes that we share and stuff like that, and
Yeah.
references that I know that they understand or like or also find funny, I'll send the same videos that kind of relate to it as well.
Yeah, so you've got like there's a theme involved. You're able to understand the theme of a video maybe from the words said, maybe from the subtitles.
Or even like similar ideas, even some comment section.
Yeah, you've read the comments. You see that the comments are interesting and funny. That like you've liked, that your friend has liked those recently with similar themes. So like bringing this back to the idea of an algorithm, like you can break apart text and search for, like you know how to do a string search. There's like a dot find, I think, on a string on a str in Python. You can go looking for keywords for sure. That's a thing that you can do. You can break apart. There's always, usually it's automatic on TikTok. They make the little subtitles for you. You can extract important words that seem interesting to you and use those to compare against other videos that you've liked, maybe, that your friend has liked, something like that. That's kind of what's happening. It's like there's a theme, and TikTok's able to understand the theme of videos that you've liked before, and so they can tell that like in the weird multi-dimensional space of where videos are that you like, they're all around here somewhere, and this new video is maybe up here. They'll know that it's pretty close to the ones that you've seen before and the ones that you liked, something like that. All right. So yeah, you've got data. You can take text apart. You can use the sounds. You can use the comments. You can use a lot of different things. You can kind of understand the theme of a video in a few short words. Maybe you can extract the most important subtitles and use that to compare against ones that you've already liked, something like that. So using previous data to predict the future, to generate likely things that might happen. That's the goal of this chapter, all right? And other chapters too, but that's where we're going. So we would like to make predictions based on the data that we have right now, because we can't predict the future perfectly, right? We know what we have, and let's use that to its fullest if we can. Okay, so like you've got a graph essentially. You've got some data. It doesn't have to be a 2D graph. It's very hard to imagine multi-dimensional things, but like if you're keeping track of, like if you're asking people for like 5 numbers at once, you're graphing that essentially in a 5-dimensional place. It's a little weird, but imagine it's 2D for ease of understanding. But the idea is we've got some numbers already. We've got x's and y's, and let's say we've got a new value. Like here's a new value on the x-axis. We got a new value here. We want to know like what's the corresponding y value for that, essentially. That's where we want. And so we want to see if there's like a trend that all the data follow, so we can kind of put that new thing. Here, let me use rainbow for comparison. Like we got this new input. Let's see what y value it's going to likely go to. Following this trend that we kind of see here, that's where we're going. It's probably going to be right there. Does that kind of make sense? That's what we would like to predict. All right. Where is this new thing going to fit on a graph? And take graph in quotes, because it's like it could be a 20-dimensional space that we're trying to graph places in. But yeah, we'd like to make predictions based on stuff that we've got. We've actually done this secretly once before. One way to do this process is like, all right, you give me a new value. Like let's say, give me this value right here. Like this is an input we've never seen before right here. What's the corresponding y value? We've never seen anything like that. Well, one way to do it is to find all the closest points that we have seen before to that one, like find the 4 closest ones, and then like do the average of that. So like maybe that is like the prediction or something. Does that make sense? That's what we've done before. So let's do that again. And the fancy word for that is called regression. We haven't said that word before, but that's going to be the idea. It's called regression. That's when you use one value to predict another value. You give me an x, I will predict the corresponding y based on things I've seen before. So the word regression has a weird history. If you look it up on Wikipedia, it's like it comes from an idea of like somebody first used it when they were studying like biology and people's heights. So it's like the heights of the descendants of tall ancestors tend to regress down towards the average. So regression was like a downward spiral. It's not what we're using it for anymore. It's just like we say regression to mean using one value to predict another. But apparently people are getting shorter on average, I guess. I don't know. We've watched a lot of tall people date a lot of short people. So maybe it's all going to even out. So that's the idea. So regression is just the idea of using one value to predict another. The history of that word, though, was meant to talk about that. All right. So we just use it to mean we're predicting stuff now, okay? So one kind of prediction is this idea, like, all right, you give me an x value, I want to predict a y value. What y value should it be? I'll go find a few close points that I've seen before around that x value. So find the 4 closest x values to this one and try to see where those were on the y-axis and try to take the middle or something, take the average. So that is called nearest neighbor regression. You go out and you find the nearest neighbors. You go to all the houses that are close by. So like you find all the close X houses, so those ones, and you just like find all the Y's that are close by. And then you take the average maybe. So yeah, that's called nearest neighbor. You have your X value, you're trying to predict something, you find the close X values, and then you average together the Y values for the group of things that are close by. And so that's kind of that right there. Maybe I should have used a different color. Because they're already blue. Let me do the exact same thing with green. Or rainbow again, why not? So here's my X value, I want to predict this. The corresponding Y value, I'll go and find like the 4 closest points on the X, these guys, find their Y's as well, and take the average of those Y's. So it's about here, or something. And of course that drew in blue on rainbow mode. Okay, good enough. So yeah, let me show this to you. We've done it already, but let's do it again. So we did an example of like child heights. We've got a child height data set, and like you say that, all right, I've got a new child that I've never seen before whose height, like with the parent's height of, I don't know, the average parent height was 60 inches or something, and we want to predict how tall that child is going to be when they grow up, when they're 18 or something. So let's go to a notebook for that. So this is prediction based on values close by, nearest neighbor prediction. We did this before secretly. You may not remember. It's been a while. But let's do it again. So it's this, it's the family heights data, if you want to go look into that. Table.read table. Family heights. Is that. And here's the kind of data that we have here. You got the family number, I guess, with a bunch of different children. Family ID. The height of the father, the height of the mother. The average is called, they call it mid-parent, but it's the average height of the mother and the father. They call that mid-parent. And then a bunch of different things about the children, but the height of this particular child of those particular parents was 73.2 inches at some point in time, maybe when they were 18, at some point eventually. Okay, so they kept track of these. And so let's use the mother and the father's height together. So let's use this idea of a mid-parent. That's the average, I guess. Or something. It doesn't actually look like the average, does it? Maybe. No, maybe it is. It's something, though. It's like some measure that combines the father's height and the mother's height. It looks like it's closer to the father's height for some reason. I don't understand why, but that's okay. Yeah. So let's use that, and I will relabel things. So let's just take those. I want to try to use the average parent height to predict the child height. That's the goal. All right. So that's what I want to do. So let's take this family heights data set, and I will relabel some stuff. You can relabel multiple things at once if you use either arrays or lists. So I can say relabeled with past tense. I like to relabel the mid-parent height because that's really long. And I also like to relabel the child height because that's very wordy as well. It's like those are the two things I want to relabel. I put them between square brackets. That's a list in Python. And then I like to call them, you give it a new list of strings. I'll call it mid-parent. This is just what the book has done. And I'll call it child. Yeah, that's what I want. And once you say that, it creates a new table, gives it back a new table to you with those ones relabeled, mid-parent and child. And those are the ones I care about. I want to just select out those. And that's the table I really want to look at right now. Dot select. Give me just those, please, mid-parent and child. So there they all are, the two ones I care about. And so I'll call this, it's a very long line, sorry, I'll call it heights. Just with the values I care about. Mid-parent is like average in some way of the two parents' heights taken together, and then the child height at when they're 18 or something. So yeah, let's see the trends. We can do a scatter plot. That's what we want to do. So like we want to kind of eventually use, like, we've got a new child, like we know the heights of their parents, but the child isn't grown yet. We want to predict the height of that child. So heights.scatter, and the x-axis is mid-parent, the average height of the children, or average height of the parents relative to the children. And you kind of see it's a little wonky looking, but do you see that there's a bit of an upward trend? The taller the parents, the taller the child. And that doesn't matter for us right now. But what we would like to do is say we've got a new child that's been born. We know that the parents are done growing. Let's say the height of the child is, or the mid-parent, the average height of the parents is 71 inches. The idea of what we would like to do right now is let's take all of the children born to parents that were around 71 inches to see how tall this child might grow up to be. So we've got all these different values. Let's just take, let's take between like 70 and 72. Let's take all of these children, right, around 71 inches tall for the mid-parent height. Let's average together the heights of the children, probably around here somewhere, and that can be a good prediction, right? A good prediction of how tall this new child is going to be that we haven't seen yet, that we don't have data on. Does that make sense? Predicting values based on close by values that we've seen before. Yeah. Oh, you want to do all this? Yeah, it's a bit long. Yeah, I'm just doing some relabeling of the mid-parent and the child heights. But yeah, once we do that, we can scatter it. So the goal is, all right, you give me a child of height, or you give me a mid-parent of height 71, like we know the heights of the parents. Let's go a little bit around that. All of these. Take all of those kids and get the average. Get the average of all the children that were born to parents around 71 inches. That's probably how tall the new child is born to parents with 71-inch average between them. All right? So that can turn into a function. We'll call it predict child. And the idea is we're going to use the height of the parents to predict the height of the child. Okay? So you're going to give me a mid-parent height. I don't know. MP height. Let's call it that. And what I'd like to do is this idea, this nearest neighbor regression. New word, but I hope you see. We're going to take the x value that we're trying to predict. We've got a new child born to parents of a certain average height. We're going to go find parents with similar heights in the data set that we know about, that we have data on. We know how tall their children were. Let's just go and find all the ones close by and use that to predict the height of this brand new child that we haven't seen before. So let's keep track of all the close points nearby this new height. All right, so go into the heights table and give me all of the ones where the mid-parent height, because that's what it's called, right? The mid-parent height, it's like the average of the parents, where the mid-parent height values are between. They're between this new value, plus and minus some numbers. So let's do like between 0.5 and like 0.5 away on each side. So this MP height minus 0.5 and MP height plus 0.5. Does that kind of make sense? This will give me a bunch of points where, like if this was 71 inches again, where the average parent height was around there. It'll go and find me all these points right there. All those points up to there. And those are all the ones that are similar in parent heights. let's go and look at all the children born to those parents with similar heights and see how tall those children were. So return, what I want to give back is give me those close points, give me the child column. So this is just the children born to parents of similar heights around, just like an inch around where we got this height, and give me the average of that, mean, not mean. So for example, again, if I was given a height of 71, like I've got a new child, I don't know how tall they're going to be, they're still a child. But I've got some data on children born to parents of this kind of height. So like, let's go around and find all these guys, take them all, and we'll take their average. That's a good guess for how tall that child's going to be. All right. So that is my predict child function. So if I were to say, I can call it now, predict child 71, it's going to do all that. Apparently, we're going to use that to predict around 67.7 inches for the child born to parents with an average height of 71 inches. It's like it took all these guys and it took the average height. And that's a good guess. Does that make sense what we did? So we did this before, but I just want to remind you of it. And we can use that for any height now. For any possible height that we could possibly care about, we want to use that to predict things. So yeah, let's take our heights table again, and let's just attach for every mid-parent the prediction that our function calculates for the child height, and see how close it was, right? We can see how close it was. See what values they were. So this is, let's take the heights table, and let's add a new column. And let's see here. Or first of all, here's what I can do is I can take the heights table and I can apply my function to it. I can take my predict child function, I can apply it to the mid-parent column. Apply heights. Well, first of all, apply the function called predict child to the mid-parent column, all the values there, and that will give me back an array. Takes a second. Give me back an array of all of the child height predictions. Beautiful. And so let's attach that as a new column. That's what I want. So I want to take that and I'll say heights dot with a new column. That's my prediction for that particular mid-parent height. See how close it was for every child. It's going to be an average though, so it's never going to be perfect, but it's decently close. And we'll call this heights with predictions. All right, and so that is that. Let's make that happen. I guess we can ask it to display itself, and then we'll print it out too. So I want to do a scatter plot. So here it is. So for every mid-parent height, like this is the prediction that our function gave back. It's not going to be exact ever because like these people had 4 children, and we're going to predict 70.1 for all of them because that was just the average around that place for the mid-parent height. Heights with predictions. If I do a scatter plot on the mid-parent as the x-axis, it will color things, which is nice. Color the other two separately. So there, that's what we did. So for every child height, like we've got also our prediction of how tall that child was going to be. And you can see that it's kind of like, you see the upward trend now, that's what our function is calculating. And yeah, it's decently in the middle of all of these nearby points. When you get out here, it's a little wonky because you don't have a lot of points. It's taken different averages. But in here, it's got a lot of data. So like, you predict the height was 70, you're going to find all these parents right here, take the average, there's the middle ground. All right, so there's our prediction. And so that's a decent way to predict a value of an unknown thing, a new child that we haven't seen before. We compare it to to children that we have seen before. All right, take the x, predict the y. So yeah, that is that function was doing all the hard work. Are there any questions about that? Does it make enough sense? So that's regression. That is nearest neighbor regression. All right. We are going further, though. We're going further, and this idea of a trend line here, where do I want to be? This idea of like an increasing line, to notice that, that's kind of the topic of this chapter. So, yeah, I want to teach you about a special number that kind of tells you just in a single value how correlated these values are. So we can say that the mid-parent and the child heights are correlated, which makes sense, right? The children's height depends kind of on the parent's height. You got taller parents, they usually have taller children. So there's a correlation there, but it's not perfect, right? There's a lot of scattering. They're not like just in a perfectly straight line. If every parent was 70 inches, every child of those parents is going to be 68 inches. That's not true, right? So there's some wobbliness, but we can have a number to represent that, all right? So yeah, a lot of the time data looks like a straight line, or you see some values increasing. Like here we can kind of see an upwards stair-stepping thing, all right? So enter the correlation coefficient, all right? It's a number that we can look at that tells you how correlated your values are, all right? So it's called R for short, just like Z was used for your how many standard deviations away from the mean was a value, has nothing to do with the word standard deviation. The correlation coefficient, I guess there are some R's in these words, but we use the letter R to represent that. All right, so they've just picked a variable name. So the correlation coefficient is a number that measures linear association. It tells you how correlated numbers are, two values are, in terms of being in line, in a line that doesn't curve, okay? Because a lot of patterns do have lines involved, like this one. It's like a straight line increasing. But some patterns are not straight lines. Some patterns are not straight lines. They look like this or something. Like this is the trend. Whee! And your values kind of represent that. Some patterns are not straight lines, but the correlation coefficient deals with linear associations, straight lines only. All right. Here are some properties of it. It's based on, first of all, standard units that we talked about before. So it's you bring everything into standard units. Every number gets turned into how far away it was from the mean in terms of how many standard deviations. That's what standard units is. The values of R are between -1 and +1, no more. So if your R value, if your correlation coefficient value is exactly 1, that means your values are on a perfectly increasing straight line. A -1 value means that your values are correlated still perfectly, but they're decreasing. One goes up, the other goes down, okay? And the 0 means that there's no linear association at all. It doesn't look like a line usually, all right? So here are some example data sets with example correlation coefficient values, and I'll also graph some too. Well, we got a cool function, but here's R equals 0 means there's no linear association. So like everything's just scattered about. There's no clear trend. Is it going this way? Is it going this way? We can't tell. Does that make sense? That means there's no association. This is 0.2, so it's like weakly associated, a little bit upwards. You kind of see the difference between R equals 0 and R equals 0.2. Slightly. And then as it gets bigger, this is positive association. So if it's a positive value, it's increasing. All right, so this is 0.5. You can see that they're in line, but there's still gaps and spread. 0.8, if R is 0.8, that means that they're more tightly packed. You see the trend better. Does that make sense? They're more highly correlated, these values, these X values and these Y values. Okay? And you bring it in terms of standard units, and you know that most things for normal distributions are between like 3 standard deviations away. That's usually your entire data set. And so you see that that's true for most of these graphs, which is fun to think about. Here is R equals 0.99. Very tightly packed, positively associated, correlated, increasing, almost a perfect straight line. Those values do go hand in hand. And then for negative values of R, that means they're still correlated, but there's a decreasing. Like when one value goes up, the other goes down. All right? Questions about what R is trying to measure? You see it? So I have a cool little function that kind of generates these graphs that I stole from the book. Let me give that to you. But yeah, this is about correlation now. Oops. Correlation is going to be fun. So here is something I'm just going to copy and paste that I don't want you to worry too much about. So this is just some code that, here, let's get rid of that. This is just a function that generates a scatter plot of a correlation coefficient of a certain value. So like here is a perfectly correlated, positively associated data set with a value of 1, with a correlation coefficient of 1 that's as big as it can be. They're in a perfect straight line. Every value is perfectly correlated. There's no wonkiness. You're never usually going to see that, but that's what it looks like. If it was a little less, like 0.8, this is what that graph is, what the data set might look like. It's just an example. It's generating example data sets. So yeah, it's a bit more spread out, but you still see the positive association. It's just not perfect, right? It's just not perfect. 0.8 though, there's still a good trend. Question? Yes. I don't really care about you knowing this code though. You'll have it after class, but yeah, if you want it right now, I'll give it to you. I barely understand how it's made. It's using some fancy math to generate a data set that has a certain correlation coefficient among the values. There, cool. Yeah, that was the right channel, right? Yeah. Okay, so yeah, you call it with 1, it generates a perfectly correlated data set. 0.8, almost as correlated. And then negative values still mean correlated, but just inversely, right? So one value goes up, the other goes down. So like here's negative 0.7. You see that there's a downward trend. There's still a decent trend. It's just downward. That's all. Okay? So yeah, this is all in contrast to like the closer this value is to 0 means it's not very associated, either up or down. So like a value of exactly 0 is just like spread out. There is no trend up, down, left, right, anywhere at all. You have nothing. Okay? So there are certain data sets, just like these family height ones, where you do see a bit of a trend. This one's not the most obvious, right? It's going to be one of the lower values, but there's going to be, you can imagine that R here is probably like 0.3 or something. I hope you can see that. Like it's positively correlated, but it's not like exact. It's not exact. Yeah, so before I teach you how to calculate R, because it's an important value, it's useful to have. It's just like you give it to an X and a Y, and it is able to give you a number that tells you how correlated they are as far as linearity goes, which is fun. But let me give you an example data set now where we can find things. So here is an example of cars. So it's this file if you want to go look at it. It's called the hybrid data set about hybrid cars. So here, table.read table data / hybrid.csv. So I think it has like the original car, like the original Prius or whatever, the first hybrid car. But here they all are. There's a bunch of rows, about 150-ish, 153. So it's got a bunch of cars. It's got the original Prius, like the year it was made, how much it sold for at the time, a number that tells you how fast it accelerates. I don't know, is this like the time it takes to go from 0 to 60 or something? The miles per gallon, and then what kind of car it was. The Prius was the first Prius was a compact car, whatever that means. I don't know my cars. So yeah, that's a bunch of stuff. What I'd like you to do is you've got a few numerical, well, you can only do correlation with numerical variables. You got a few numerical variables, a few numerical labels in this data set. Try to read this table. Here's my question for you, Fresh Dice. Try to take this table, make some scatter plots. All right, make some scatter plots and see if any two variables have some correlation with each other. And we'll see what you think. And see if two variables correlate with each other. And then we'll try to calculate R values eventually. But you got a bunch of numerical values. Try them on the x-axis and the y-axis. It doesn't really matter because the R value doesn't change if you flip x's and y's. It's still positively or negatively associated, but you got some numerical values. Try to, probably year is not the most useful one, but try the other ones. Try some graphs of their combinations and see if you can notice any trends. Are there any things that are correlated? Take my thoughts away, but I have some ideas that I will talk about after you try. Maybe I'll give you like 2 minutes to try that. It'll be hybrid.scatter, and it's the hybrid.csv file in our code from class. Dun, dun, dun. Alright, almost stopped it in time. My thought is surely the more expensive the car, the faster it goes, the faster it can speed up. So I feel like there's got to be a correlation between MSRP, the price, and acceleration, surely, right? So it depends on which one you want on your x-axis, but I'm going to try that one first for sure. Let's see, acceleration. So if acceleration is on the x-axis, MSRP on the y-axis. So let's see how faster cars maybe are more expensive. Yeah, that surely seems like a increasing correlated thing. Yeah? Did we notice that too? That's a good one. What other ones do we find? Any other good trends we saw? What other ones do we have here? We've got miles per gallon for sure. Probably is important. We can do that in terms of price again, maybe. How about that? What do we got? MPG on the x-axis. Surprisingly, the more fuel-efficient cars look like they're costing less. Very interesting to me. I don't know how to feel about that. I'm not really sure how to interpret that. But I guess, like, you buy a hybrid car and it's expensive. Maybe you just want it to go really fast. And to say that you drive a hybrid and go in the carpool lane, you don't really care about your miles per gallon at that point. It's just like, I don't know. There's a word for that, maybe. It's like you just want to look like you're helping the earth, but you're not really. But yeah, I see a downward trend here. An interesting fact is I don't think this is a linear trend here. Do we see that? This does not look like a straight line. If I wanted to draw something that connects these, I'd probably go like this. Like, you see that? It seems like it's a non-linear trend. Interesting. Very interesting. Food for thought. So there's more to the world than just linearity, but you can still try to draw a line between these and you'll still see that's going to be negative. So still the correlation coefficient will give you some information, even if it's not a linear thing that you're noticing. So that's still good news. Let's do, for some reason, if we look at the SUVs, then we get something interesting. So here, let's do a sample so I can show you all the different values. Some of these are SUV, compact, two-seater, but apparently the SUVs have more of a linear correlation in terms of miles per gallon and other things. So let's do that. Let's just get the SUVs and deal with them right now. For some reason that works better for my purposes right now. So go in the hybrid where it's the class of car is an SUV. Give me that. And let's do a scatter plot now for those where it's MPG on the X and MSRP on the Y. And this one, still a downward trend, surprisingly. Maybe the more expensive cars are also bigger. That would also make sense to me. Like bigger cars made of more metal. They're not going to have as good of miles per gallon. So there's a trend here. This looks more linear though. All right, so let's use that. So you got that one, and then same for acceleration is still a good trend there. Acceleration and MSRP, that's still a good upward linear trend. If you try to draw a line, you can see that like they're all going to be close to one another if you try to draw a line between these. So before I show you how to calculate, oh gosh, do I want to do this now? Yeah, before I show you how to calculate the value of R, this correlation coefficient, we would like to bring our values into standard units. I'm going to bring them into standard units because that's going to help us calculate. That's part of the formula for R. I just want to show you that if we were to turn acceleration into not like seconds and MSRP not into dollars, but into standard units, which is just like standard deviations away from the mean, how many, that is not going to change the graphs in any meaningful way. It's going to keep the dots in all the same places. It's just going to use new units. That's all. Okay? So let me do that for us. So let's make a function called standard units that turns any array into the values in that array. It gives back a new array with those values in standard units. So if you give me an array of numbers, I'll call them nums, then I'm going to give back those numbers in standard units. So here's how you do it. I'm going to return back. You take the numbers, you subtract how far away they are from the mean, so minus np.mean on the nums. That's just one value. So these are all the numbers, how far away this will generate the array of all the numbers, how far away each of them are from the mean of those numbers. And then what we want to do is know how many standard deviations away from the mean are they. So we're going to divide that by np.std. It gives us the standard deviation of those numbers. This is like, all right, how far are the numbers away from the mean? And then we divide by the standard deviation to tell us how many standard deviations then are these numbers away from the mean. Is that coming back to us? Remember that? Questions? That turns these numbers into standard units, okay? So instead of our acceleration values being seconds, we'll turn them into standard units. How many standard deviations away from the mean are they? All right. So I can do that now. I can say, all right, give me SUV dot column, give me the MPG column. Here are all the values there. I can turn those into standard units. I can say standard units now on that array. Okay, and these are gonna, they're different now. Just like the first value was 1.32 standard deviations above the mean. The second value was about half a standard deviation above the mean. Some of these, like the last value, is about 1 standard deviation below the mean. That's what it got turned into. These are the units now, standard units, okay? But let me show you that when you do that, it does not change the graph. It just changes the units. So let me attach this to the SUV table. Or just, I'll make a new table, I guess. Make a blank table. I'd rather add it to the table. So here's my SUV table. I like to attach to this, just to show you. Let me select out the MSRP, or sorry, yeah, MPG and MSRP. So we've got this one and this one. That is 0, 1. I guess I'll just do it like this. MPG, MSRP. So these are the values. Let me attach to that table those values in standard units. Okay. So let me do that. Let me add some columns now. Take make a new one called MPG in standard units this time of that one, and that will be standard. It's exactly this here. Give me that one, put it there, and then let's do an MSRP in standard units, and that's going to be take the column from the original table. That's called that. And that will generate the following table. Ta-da! And so instead of 31.99 miles per gallon, it's 1.32 standard units above the mean for miles per gallon. All right. So they're turning into these numbers, and I'm going to graph these numbers now. Okay. So, okay, let me do those scatter plots all over again. We've got, let me just do one of, I guess we'll do both. What's the easiest way for me to show you them all at once? Let me just make a new blank slide, and I'll copy and paste them. That would be the easiest way to show them all at once. So here's the first one. Can I copy this whole, like, image? Copy output, maybe. Is that a thing? That's a thing. Cool. All right, there's that one. That was the first one. MPG and acceleration. And then we got this one, MSRP. Acceleration and MSRP. The first one was MPG and MSRP. So this was in normal units. Then I'm going to show you these graphs in standard units. Where you go away? There. Cool. So there's those. Let me turn them into standard units now. So I'm going to take these now and graph them. So let's call this table, I don't know, SUV2 is that. And I'd like to do a scatter plot now of these ones. So we've got MSRP, MPG. I guess let's do the same for acceleration. Dun, dun, dun. While we're thinking about it, acceleration in standard units. There, now I've got them all. Standard units values, original values. All right, I'll call that SUV2. And so SUV2.scatter. Scatter, let's just use the normal column name. So the first one we did was MPG and MSRP. So MPG in standard units is 0, 1, 2, 3. Scatter on 3, and the Y is MSRP, which is 4, then index 4. 0, 1, 2, 3, 4. 3, 4? So it looks like that. And gosh, what's the easiest way to show you? So you know that for normally distributed things, the values are always going to be between -3-ish standard deviations below the mean to +3 standard deviations above the mean. So I can stretch the graph like that. X limit from -3 to +3. This is just something that your book did. The Y limit, do the same. Usually that's as wide as you want it to be. Semicolon to suppress the output at the end. But here, I'll copy and paste this. Dun, dun, dun. Do you see that the graph is just a little bit stretched, but there's no real difference? I've turned them into standard units, and so they're all on like an even playing field with one another. They're stretched a little bit, but you still see that there's a downward trend. See how you see all the same dots and pretty much the same places, but like that one got a little squished, so that you're still going by the same amounts of units here. So you're not jumping over as fast, kind of on the x-axis. So yeah, that's that graph, and then I'll do the other one. It was acceleration and then standard units. And acceleration is 0, 1, 2, 0, 1, 2, 3, 4, 5, index 5. Still MSRP. So 5, 4. I think that's right. Cool, acceleration to MSRP, both in standard units this time. Notice how the graph is exactly the same, just a little stretched maybe on the X or the Y. See all the same dots in all the same places. You see all these guys, they're still there. No real difference. But putting them into standard units gets everybody on an even playing field where just like how far away from the mean are all these values. And this is the first step towards calculating the R value, the correlation coefficient. Because you see that there's a downward trend here, so this should be some negative R. Eventually, we'll get that, right? Some R should be negative there, R should be positive there. Same is true for the original graphs, okay? Yeah, so that's the correlation coefficient in a nutshell. It's just a number that tells you how closely these values are correlated in terms of lines, okay? So yeah, that's almost 1. That's pretty much a line. -1 is just a decreasing line. 0 means there's no correlation at all. So yeah, I think that's what I wanted to say for those. Any questions about the correlation coefficient before I show you how to finally calculate it? All right, so here's the secret. Here's how you calculate R. What you do It's very interesting. I can't explain in math easily why, but the R value is calculated by taking the average of, first you do the products of the two variables, the x's and the y's that you were graphing, when both of them have been turned into standard units. So you take your acceleration values and your MSRP values in standard units, you just multiply each of them together. Each of those pairs of values that you were graphing, you're just multiplying the x's and the y's together. You're adding them up and dividing by how many, because you're taking the average. You're taking the product of all of those variables, and then you're taking the average of all of them. Okay? So that's the idea. That's it. And just remember that it only measures linear association. It's going to tell you how close these are on a line to one another. So like you're going to get a good R value for this graph, because that's pretty much a line. You're not going to get a very good R value for this graph, but it's still going to be positive, I hope you see. It's going to like try to do its best to draw a line, like the best possible line between these. But you see, it was supposed to have been a curve, right? This one is probably going to have an R value of 0, because like they'll try to draw a line that's probably the best line between them all, yeah? Even though you see that there's a clear trend, it was not a linear trend. So you do have to be careful. Look at the scatter plot first, or second. But it's still a useful number because a lot of things in the world are linearly associated. They are correlated in that way. Okay? So yeah, it's gonna do its best, is what it's gonna do. All right. So you get the products of the variables, get them in standard units, take the average. That's R. Boop. All right. So let me just give you a simple example with just a few points. Here's some x values. Here's some y values. Let's do. The x values can be all the numbers between 1 and 6. So 1 to 7 increasing by 1. And then the y values for each x will be 2, 3, 1, 5, 2, 7. Okay, so I'm going to make a table with x's and y's now. Table with columns. The x values are the x array. The y values are the y array. And I'll call that table just T for short. So there's my table T. It's got a bunch of x values and their corresponding y values. These are just in like original units. They're in inches and seconds or something. I don't know. Okay. Price, dollar. The first x is in seconds and y is in dollars, pretend. Okay. So we can do a scatter plot of these. For some reason, your book chose to use red here, so I'll show you how to change the color of your scatter plot. So I'll scatter on x and y. So in 0 is the x, index 1 is the y. You can make larger dots. So like the default is this. For an interesting reason, your book is going to teach you now. I'm not going to force you to memorize this for a test or anything, but like if you want to make the dots bigger, it's S for size. Like make them size 42. Now they're a little bit bigger. Make them size 100. Giant dots. Bless you. So big dots now. And then you can also change the color of the dots by saying color equals something, some string. So they're now red dots. You don't even know that, but now you know. Okay, so there's those. Those are my values. And what I'd like to do is calculate. You see that there is a linear trend for these values, yes? Increasing linear trend. If you try to draw a line, it's probably going to go in between. Something like that. Just like that. And so, bless you. We've got positive correlation value. R is probably like, I don't know, 0.5 or something. So let's calculate the R for this small little data set. These x's and these y's. Let's calculate R. And so the very first step is get these values, not in their original units, not in like dollars and seconds, but in standard units. How far away are each of these values from the average of them in terms of how many standard deviation jumps are they away? Okay, so we got a function for that. We will just call that on our arrays that are our columns. This converts everybody into standard units. I'm just going to give the first column to that, get it back, give the other column to that, get it back as well. So yeah, let's take these. So I got my T table. I want to make a new table. So T dot with some new columns. I want the x values in standard units. How far away are the x values from their mean in terms of how many jumps of a standard deviation? So take the standard units, and it was the x. I already have the array. I called it x, so that's perfect for me. And then do the same with the y's. Y standard units. Boop. And so that is this table. So instead of x's and y's in normal, like dollars and time, we've got standard units. This x value was negative 1.46 standard deviations below the mean. So 1.46 below the mean. This one was 1.46 above the mean because it's kind of centered. Hopefully you can see that. And these y values are similar, but in terms of those, like 7 was a very big value. It was 1.78 standard deviations away from its mean. So this is, I'll call this table T in standard units as well. TSU. So there it is. And so now to produce the R value, I'm going to take the product of each of those values just in each row. So I'm going to multiply this by that, this by that, this by that, all of those guys multiplied together. And I can make a new column of those. So that is TSU dot column number 0, 1, 2. That's the first one. That's the x's in standard units. I just want to multiply all those values by column 3, right? That's the y values. 0, 1, 2, 3. Give me all those y values. So corresponding ones, multiply them all together and give me that array back. And so I can shove that into a new table. T product equals TSU with a new column called product of standard units. Something like that. There it is. And T product looks like this. So each of those values, the negatives cancel in the first one like that. Produces that. That. And sometimes it's negative, and one's positive, the other's negative. You can maybe see how that's going to give you, if there were a lot like that, and you got a lot of negative values, that would give you a negative correlation value. Interesting. And then so we got all these products, and we just add them up. We add them up and we take the average. So divide by how many as well. So take the average of all these products. That's the final step. All right, that gives us our R value, our correlation coefficient. So yeah, the R value is R equals, just give me that column and take the average. So it's T product, that's the table I called it. Give me column number, product of standard units. So 0, 0, 1, 2, 3, 4. Give me column 4 and give me the average. So I can do this in a million different ways. Dot mean would do it, np.average would do it, or np.mean would do it. Okay, either way, any of the ways. And so give me the average of those products of the values in standard units. R is equal to 0.6-ish. And so that's a decent upward trend for those points. Does that make sense? Questions about how we calculated it. Got the values in standard units, took their product, and took the average of that. That miraculously, due to some very cool math that I cannot explain, gives us a number that describes how linearly associated these values were. Thank you, excuse me. So yeah, that is R in a nutshell. That's how you calculate it. Okay. Let's see, what else do I want to do? Yeah, so I think that's a good start for sure. So yeah, that's the formula. It's going to give you a value for R. Tells you how linearly correlated these values are for your x's and your y's. Okay. So that, I think, is most of what I wanted to say. So this process now we can turn into a function. We can call it correlation. I want the correlation coefficient. I'll call it def correlation. You give me a table, and you give me the label for the x values, and you give me the label for the y values, and I will give you back the correlation coefficient of those x values and y values, because I know what to do, right? It's going to be take the x values and y values in standard units, multiply them together, and take the average. So first, get them in standard units. That's step 1. So give me the x in standard units. Standard units. I got a function that does that. For the x's, give me standard units for the y's. I got them now, right? Then I want to multiply those values together. Got an array, 2 arrays. Multiply them together, right? Multiply those together. It's where x and y are the labels of the table. So it's t dot, give me the column labeled x. And it's t dot, give me the column labeled y. Something like that. Okay, so give me that column labeled y, give me that column labeled x, turn them into standard units. Oops. Turn them into standard units, and then multiply them together. Of course, I can't use my mouse. Multiply them together, the products, and then take the average of those products. So this whole thing now is one big array, all the products of the values in standard units, and then I want the average, np.mean of all of that. That's what I return. So that is my correlation function. So I can ask it now. I had my table called originally, it was just t. Give me the table t, the label was x's and y's. Give me their correlation values. On my original table was actually called t, and it was x was the label and y was the label. So it does that same calculation, and it's symmetric. So it didn't matter that it was x's on the x-axis and y's on the y-axis. You could have flipped them, predict x's in terms of y's. It's going to be the same value because multiplication, you know, is a commutative operation. Does not matter who's first, who's second. Same value, doesn't matter who's on what axis. So yeah, that's correlation in a nutshell. And so now we can go back to our graphs and see like what they were for the SUVs. Are you ready for that? Any questions about like this calculation before we go there? This is fun. All right, so we had, well, what do we got? We had, for the original table, it was SUV table, it was miles per gallon and MSRP. So that was, give me the correlation for the SUV table where the X label was MPG and the other label was MSRP for Y. What was that correlation? It was negative 0.67. So that is our downward trend right there. You see it. Boop. Negative trend, decently linear, decently correlated, negative 0.6. So the downward trend, when one goes up, the other goes down. Does that make sense? That's nice. We got a number that proves that to us. That's cool. Then we do the same for acceleration. It was acceleration and MSRP. What was that correlation? And you know that it's going to be the same. You didn't have to do it in this order. Like the MSRP could have been on the x-axis. Okay, so this one was not quite as correlated, but it was positively correlated because it's a positive value, about 0.49. 0.49, so a little bit less correlated, but still increasing decently. All right, decently linear trend there, decently correlated. So yeah, that's the R value. Now you can compare R values. Like the miles per gallon correlates better with MSRP than acceleration does. We can say that now. That's kind of cool, at least linearly. So that's fun. Any questions about any of that? You see it? It's a cool little value. That's really nice. Remember the goal, first of all. The title of this chapter is prediction. I don't want to get us off track. Like, this is interesting and cool, but the goal is we have this line now. You give me a new value that we haven't seen before, I can put it on the line. That's my prediction. Does that make sense? That's where we're going with all this. We need to take some time to get there, of course, but like that's the goal. So, all right. Dun, dun, dun. Let me show you that it doesn't work for certain things. Like when it's nonlinear, it tries its best. It draws a line, tries to draw the best line, but sometimes that's useless. So here, let's make some new x's and some new y's. All right. My new x values will be between -4 and +4. -4 and +4, so I gotta go like 4.1 or something. And we'll go in increments of 0.5. So those are my x values. And the y values, I'm gonna graph the equation y equals x squared. So that's a parabola. That is not a line at all. So let me get some nonlinear y values, or nonlinear table. We got a table with some columns that have, like, on the x, we've got these new x values. And then on the y, we have y equals x squared. So take the x values and square them all. That's my nonlinear table. So every y is the x value squared. So I'm graphing y equals x squared in terms of those. And so I want to scatter those. Scatter x's and y's with some large dots. S equals, I don't know, 55 or something. Some large red dots. Color R for red. Cool. So there's my graph. This is not a linearly correlated set of values, right? It's correlated. It's got a nice, it's perfectly quadratically correlated, I guess you could say, but it's not linearly correlated. So the R value is going to get very confused. All right, so let's ask it. Hey, how is X and Y? Are they correlated at all linearly? You got to remember that word linearly when you ask for correlation coefficient. Because these are for sure correlated, it's just like not linearly correlated. So for this nonlinear graph, how are the X's and the Y's correlated? What's the R value? The R value is exactly 0, which is funny because it's trying to draw essentially this line. It's like, all right, that's the best line between them all. Something like that. So it's exactly 0. It's saying these values are not correlated at all, but we see that they really are, just not linearly correlated. You see that? So that's important. So that's one way to mess things up. You didn't look at the graph first. It's not a linear correlation, but it's still a correlation. You'll have to try something else, some different values. What else? You could also be thrown off by just one bad value or a couple of bad values. Like this is a linearly correlated thing. We could have had it worse. Like we could have had something that's linearly correlated, but just like we got a bad reading from our sensor or something and it threw everything off. So let me show that to you. So that's where you have an outlier. Somebody's just out of the graph in a weird spot. So outlier. It's mostly this. Let me make a new table that looks similarly. So I'll call it outlier. Outlier looks like this. So the X values are, let's make an array. I'll type them out. The X values can be 1, 2, 3, 4, 5. And the Y values associated with each X value are going to be 1, 2, 3, 4. So perfectly correlated there. And then this one, instead of 5 here, I'll put it 0. So I'll say outlier dot scatter X and Y in the same exact way, actually. So here is pretty much every value is perfectly in line except for that last one. You see it? That's our outlier. That's our bad value, our bad reading. Something went wrong. That can also throw you off if your data set's very small. Or this is a really extreme outlier, one way or the other. So what's the correlation between X and Y right now? You'd think it's like perfectly 1.0 for all those other values, right? Correlation dot on the outlier table for the X's and Y's. I chose this perfectly. This dot right here made it 0. Not correlated at all is what it's saying. You see that? But we know it to be correlated, so maybe you should be getting rid of your bad values. You can be like, if you think you have an outlier, maybe you don't include that when you're calculating your things, like outlier.where the X values are below 5. So to get rid of that one. Now they're perfectly correlated with 1.0 with all the other values. See that? So maybe you got to process your data a little bit to get rid of any potential outliers, but you have an extreme value that can throw everything off as well, even though it was linearly correlated. Disgusting, I know. So yeah, I think that's most of what I wanted to say. Are there any questions about that? All right. Let's see. How do I want to do this? Well, first of all, remember that R is giving you a correlation value. It's not a causation value. We've seen this before. This is on the x-axis. We have chocolate consumption, kilograms per year. That's a decent amount per person. And then we have on the y-axis how many people won a Nobel Prize in terms of a certain amount of people. So it looks like the Swiss, of course, they love their chocolate, and they also have very smart people. So like they're way up on this graph. But do you see that there is a linear trend between chocolate consumption and how many people get a Nobel Prize in a country? Interesting. Maybe that means we should all be eating chocolate. I don't know. We're on this graph, but not high up. So yeah, maybe we should be up here. But you see that there's a very strong linear association. The R value is almost 0.8. Amazing. But that's all we can say is there's a correlation between these values, right? We have not done a randomized controlled experiment. That would be very hard to give you a randomized controlled experiment because you'd have to have people, some of those people in your data set have to win Nobel Prizes. That's very hard to have happen. So we'll probably never be able to fully understand this, but This is a correlation, not a causation. Remember that. Okay. So, yeah, let's see what I want to do here. I guess I have a bunch of questions for us. I don't think we'll be able to get through all of them in a row, but we can start with the first one, I think. So, in addition to our child heights data set, there's just one on parents and their like the parents and their sons only heights. So, let's try those. All right. So, here's my question for you to get started with this, and I'll come and I'll do it with you as well. But I think that would be a good start to everything. Let's do let's read in the sunsheights.csv file together, just to get some practice with correlation and stuff. So oops, I want this as that one. So let's read in this table together, and then I'll show you what I want. And then we'll come back and do the other ones next time. So it's sunsheights.csv if you want to read that in. And I want you to read it in, I guess. So there it is. It's a different heights table. So we've got father's height, mother's height, son's height only, this time in inches. So what I'd like you to try is you've got three variables, father height, mother height, son height. See how each of them correlate with each other. Because like you can even try father and mother's height, because maybe like taller people have kids with other tall people. Like that could be correlated in some way. So try to look at all those variables. Try to calculate the correlation coefficients of all of those. Here, if you want, let me give you all the things we've done so far on the code from class. If you go to the code from class from any other link, I'll give you today's stuff right now so you can go look at it. And of course, I'll give you the rest after we do this too. But if you go to any code from class page now, chapter 15 this is available for us. So you can get everything that we did, including all of our functions. So give this a try. Take a look at these sons heights data sets. Try every label, father, mother, son, see how they correlate with each other, and draw some scatter plots. Try to calculate the correlation coefficient of all of these. You can use our special function if you want, just to like get started, but I'd like you to try to calculate correlation the hard way. Like do the function's job yourself at least once so that you can kind of ingrain in your brain what's happening. Like, okay, we got to convert to standard units. Okay, we got to multiply. We've got to take an average. Okay, so try all those things, and yeah, I'll give you a few minutes to do that, and then we'll come back together. I'll show you my way, and that will be it for the day, in terms of the lecture at least. I'll give you 5 minutes to try that. So your labels are father and mother and son. So it doesn't matter in which order you do them. So there's like these are the three different ones that you can track. Right? Father, mother, father, son, and mother, son. I split them the X and Y and Z doesn't change the correlation. Try them all, see which ones are the strongest, and then for maybe the strongest one that you find, try to calculate the correlation the hard way, the long way, the way that doesn't use any of our functions. Let me know if you have any questions. Oh, looks like about 1 minute left. I'm going to stop the timer so it doesn't make noise. All right. Did any questions come up as we were trying this? What's the best? Which variables are the most correlated? Did we find? Yeah. Was that? You agree? Yeah, father and son. Let's take a look together. Nice. I think that is right. Where was I? I was here. All right. We've got. Let's do a little scatter plot. So son's heights dot scatter. What are the other options? Let's do the other options first. We've got father and mother. It looks like there's not a ton of correlation there. We can also have it print that out after it does it. Correlation. Son's heights on father and mother. So it looks like there's a very weak correlation. It looks like some usually very weakly taller fathers have children, have sons with taller mothers. Very weak though. It looks almost close to zero. So it's not super correlated for father versus mother. What about mother and son? I think it would make the most sense to like predict the son's height. Put that on the y-axis, and the correlation of that we can also calculate with our little function. That one is 0.31 correlated. Nice. It looks like taller mothers have taller sons. Makes sense. And then finally, we can do father and son. And that one is 0.5. That's the best one. That's the best one of the three options. And you can see a decently strong linear correlation there with a taller father ends up having a taller son. Cool. And so we have that correlation value. And if you wanted to do it the hard way, what do we got? We got to calculate the R value. That is, get everybody into standard units, take the products of our variables, and then take the average of those products. So doing it as arduously as possible. How do you get the father column in standard units? Because it's called son's heights, right? That's our thing. We can get the father column. We can convert it to standard units by saying, let's see, we can call it like father heights. Give me that column. we can convert it to standard units manually by saying like father in standard units. That's going to be equal to, right, to calculate standard units, you're going to see how many standard deviations away from the mean each value was. So it's take every value in father heights, see how far away from the mean they were, minus the mean, father heights, np.mean of those. And it's not just that, not how far away the mean were they, but how many chunks, how many steps of a standard deviation away from the mean were they. So it's all this divided by, then, the standard deviation on the father heights. So that's the father heights in standard units now. Does that make sense? That's how you can calculate it the long way. We do the same for the sun heights in standard units. I'll just be lazy and use our function for that, but we have, it's called standard units, right? We made that function on, what was it? How do we call it? We give it the actual column. So give it the columns. This is slightly saving time, but you can do it the same way again if you want to. This is just me getting a little bit faster. So now I got all the father values and the son values in standard units. I want to multiply them together. Right, that's the next step, products. I want to multiply each of those corresponding values together, and the NumPy library lets me do that quite easily. I just say star, like I was doing one thing only, and it does it for all of them. And then I want to take the average of all of those. I want to take the average now. So np dot mean of that multiplied thing, and we get the exact same value. What do you know? Nice. So that's the correlation value, and that is, I guess, that goes to show that for every son, they're more related in the height of their father than their mother. Good to know. And it's almost not useful to compare the heights of the mother and the father together. Those didn't correlate very well, we saw. So yeah, that was that one. Does that make sense? Are there any questions? So that is our first intro to correlation. I think that's a good place to stop. I have some more questions that we can start with next time. We can play around with things. But remember that correlation is not causation. Remember the goal here. Like, we're trying to be like TikTok. What we would like to be able to do is this R value is essentially drawing an invisible line for us right now. We'll eventually create the line physically, and we can use that to predict things. Like, you give me a new value, a new X value, I can look on where the line was supposed to have that Y value. That's like going to be the best option for where the Y value should be, is it along the trend line that the R value is trying to measure here. Okay, so that is where we're going, but it will take we'll take another lecture to get there, I think. So yeah, I think that's all that I wanted to talk about today. Are there any questions about anything before I stop the recording? All right, that is all I got.